Okay, all right. Do you guys see my screen? Okay, great. Okay. Some of you have submitted the assignments, and some of you have not submitted. Uh, but just wanted to understand if you have any kind of difficulties. So this is the assignment that we have that I have given. Let's go quickly go over it. So the first thing is basically explain the mass operation with diagrams. So I would expect you to, write all the three stages or the three modes of operation. So you guys know that cutoff, linear, and then saturation with diagram. So that it would be, remember what how it actually operates. Okay. Uh, Now the next one is basically what is meant by width and length of MOSFET. Okay, explain with diagram. So for this particular thing, what I would have expected is this particular picture. So this is the particular picture that I would have expected. Say for example, what is the meaning of length? This is the spacing between the source and the drain. This is what we call it, kind of, no, the length. And it is the width is something, like this. Okay. And so this is the picture that I would have expected you to draw. And the next one is how delay varies with length and basically width and length of a transistor. I think we discussed about it, right? So how delay varies. So if you look at your L decreases, your delay decreases. So L is basically, delay is directly proportional to L. Now in case of width, okay, when width increases, your delay decreases. Okay, so this is what I would have expected, and the reason, probably, if you know what is the reason behind uh, this relation, okay, that is the answer for this third question that I would have expected. And the next one is basically what is threshold voltage, and it depends on what parameters. So ideally, if you would have looked at it, right, so threshold voltage is basically the voltage at which the transistor is said to be turning on or operating. Okay, and it depends on various parameters. So if you'd have done a little research on it, you would have definitely got it. Okay, and the next one is basically what is static power and what are the different components they get added. So I would have, so these are all the one which comes under the static power, and I would have expected you to explain what is the meaning of static power as well. Okay, so basically that's a leakage or probably the power consumed when the transistor is said to be in off condition, or probably it is not in the on condition. Okay, excuse me. So the reason why I gave this question was because in industry we look at reducing your overall static power. Okay, now, so the next thing would have been like kind of, if you'd have gone little above, right? I mean, probably little research on this, you would have learned about something called HVT, SVT, LVT. Okay, so this is going to be say something like multi-VT libraries. So though we talk about static power, now how would you reduce your overall static power? So basically your leakage. So for that, if you wanted to do something like that, if you wanted to reduce your overall leakage power, then you would definitely need something like kind of multi-VT libraries. Okay, and the next one is basically the dynamic power. So short circuit power. What is the meaning of short circuit power? So how would you reduce your short circuit power? So we know that short circuit power meaning it is basically when you say CMOS, you have both PMOS and an NMOS. Okay, say this A, say this Z. Now when one of them is turning on, so basically usually both will not be on at the same time. It would be like kind of this may be off, this may be on. Okay, so now assuming A is 1. Now say A is turning to 0. Now what will happen? This guy would go from off to on, and this guy would go to on to off. Now during this process, there would be some time where there will be a direct path. Okay, now during that time, whatever the power that actually gets consumed, okay, that is something that we call it short circuit power. Okay, so now how do you reduce it? Remember, the short circuit power can be reduced, but so when the short circuit power would be on high, say there is something called transition. So there's something that we call slew or transition. Okay, now this transition can be say 200 PS. Okay, or so there could be a transition say 500 PS. Now, out of these two, which is going to have more short circuit power or which is going to consume more short circuit power? Any idea? Okay, great. Yes, because the amount of time it takes, if the transition or the slew is longer or probably on the higher side, then obviously the amount of time this short circuit path, okay, will be or longer. So the power would be consumed kind of during that time would be kind of higher side. So if you wanted to reduce your uh, short circuit power, then basically what you should do, you should see if you are having a proper transition that for your design. Okay. Now the next one, what is switching power? Okay, switching power, you guys know that so any circuit that you take, there would be kind of load that gets added. Say for example, this is your inverter. Now say assume there is a fan out of 4. So this Z is driving fan out of 4. Now there is a load that gets added that automatically forms. It is not your wish. It automatically forms. Okay. Now C load. The C load is basically C pin. Basically the pin capacitance of all these guys. So if you look at here, the pin capacitance. So this pin capacitance and this pin capacitance. So all the C pins, basically you have n number of fan outs, and all of them would be added here. Okay, C pin plus C net, the net that you are going to route. Okay, so eventually when you say 0 here, your output would be kind of PMOS is going to be on, and it is going to charge this load cap. Okay, now that is basically charging. Now say all these guys will be seeing logic 1. Okay, now when you say if it is 1, what will happen? This becomes on and this becomes off. Okay, now what actually happens is it would actually discharge completely, and when it gets discharged it would be completely kind of say 0. The logic would be 0. So that means the next inputs, okay, basically the fan outs, they all would be kind of having a logic 0. Okay, so now during this process, right, so charging and discharging, okay, of this capacitor is what actually happens. Now the power that is consumed during the whole process is called switching power, and we discussed this in detail also. So overall power we talked about, I think, P static, you guys know all the leakages components. Okay, P short circuit, so it's basically your VDD into ISC, short circuit current. Okay, and your P switching is equal to alpha C P squared F. Okay, now this alpha is nothing but your switching activity. So how many times in a clock cycle this is actually switching? Okay, now this cap is nothing but your load cap, and then V squared, it's basically your voltage. Okay, and then frequency. Now let me ask you this way. Say there is a design 1 which operates at 500 megahertz. Okay, so there is a design 2 which operates at 1 gig. Now which one will consume more power? Which one will consume more power? Reason? Okay, great. Now remember, if you are working on 3 gigahertz plus designs, what will happen? Your power would be very high consumption, your the overall power consumption, right? So now, okay, so let me ask you, what is your frequency of your CPU in your phone? So I'm sure everyone is having a smartphone. What is the frequency that is actually targeted or probably designed, the chip inside your phone? No, give a guess. Take a guess. I'm not going to lose anything, but I need you to justify that. Okay, so here you go. Yeah. So there are different things. Minimum two. There would be a minimum two. Okay. If you go and take a look at it, so you will have minimum of 2 gig. See here, the architecture is something that is people call it like kind of, this is your octa core. If you look at, this is your octa core configuration. Okay, that means 8 CPUs in the chip. Now out of 8, so this 4 1.8 gig. Now there will be 3, which is kind of 2.4, and there will be one more, which is 2.84. Okay, so if you look at this is 4, 3 plus 1. This is the kind of configuration that each smartphone ICs will have usually. Okay, now if you go and ask me, does all the smartphone ICs will have this? It depends. So you need to look at what is the spec and everything. But this particular thing, Snapdragon 875 is kind of having this. Now, so this is kind of octa-core. So I worked in MediaTek where we had a deca-core. So that means, so 4 plus 4, which is kind of 1.8, and then I do have another 4, so which is kind of 2.2, and I do have kind of two big cores. So it is going to be kind of 2.8. So this is something that we call it deca-core. Okay, so what is this meaning? So now you need to understand, when you are designing a CPU, your power is going to play a critical role. So you need to understand your switching power. Okay, and you know that now, targeting higher frequency will eventually lead to higher power consumption. So the team, in case if you get an opportunity to work on CPUs, that is the best thing that you can ask for. Okay. So any question here? So the switching power is going to be this. Now getting back to our original thing. So your total power is going to be combination of, so this one, two, and this three. So those total. So this is what going to be the total power consumption. Okay. So I would have really liked had you gone to this level. Okay. Any doubts here? I know I'm trying to help spend some time on assignments, but yeah. So here we have written, like, the question is like, how do you reduce overall power dissipation and etc. Okay, the next one is basically what is mean by strong zero and strong one, weak zero and weak one. So we know that individual MOS transistors, say for example NMOS. So NMOS gives what? NMOS gives what? Okay, so NMOS gives strong zero and PMOS. Next, is that give strong one or weak one? Okay, weak one. Now, what about PMOS? Okay, strong one and week 0. Okay, so we would prefer always both case strong. So which is going to be kind of, you know, so NMOS at the bottom, PMOS at the top. So that is the reason we have something like the circuit like this. Okay, so this is something that we call it pull up, and this is something that we call pull down. Okay, the reason behind why PMOS is on the top is this strong 0 and strong 1, and NMOS in the bottom or probably in the lower section. It is because it can give you strong 0. Okay. Now I also we have discussed about pos transistors, and then uh, we tried solving some problem in the last class. So based on that, I would have liked if you would have explained the the assignment, if you have written the assignments. Okay, and as I said clearly, so you need to write your assignments in A4 sheets or long plain notebook only, and you can refer these all before in case if you are going to give interviews. Okay, so these are all the things basically. Imagine now, so many of you are kind of passed out, fresh passed outs, or maybe it's recently passed out and etc. So the reason why I'm focusing on this mass this much in depth is, say there is a one opening. Okay, now if when they announce this one opening, there will be 1,000 plus resumes. Okay, there will be different category of people. Now, so assuming your resume got shortlisted based on your basic criteria. Now next is your written test. Okay, now written test could be aptitude. So basically your digital. Okay, and sometimes you might have CMOS, and then you may have PD or other domains, and then aptitude. Now, so assuming you're clearing of this also, now the next thing is you you might be attending going for a face-to-face interview. Okay, now this person who's going to take your interview, as I mentioned in the past also, may be from different backgrounds. So he may be from DFT, or he may be from PD, he may be from verification or any domain. As freshers hiring, they would actually kind of target only the basics kind of thing. So let's say if they come and ask me for, let's say, Kumar, I have we have a scheduled drive. Would you be available next Saturday or something? If I have office work, or if I am already occupied with occupied with any of the previous or you can say my scheduled work or any of that. Now I may not be available, so they have to go ahead and find someone who will talk to the candidates and choose them. Now, so mass is the topic that you can easily defend yourself irrespective of anything. So digital and CMOS is the topic that everyone should know, irrespective of whether you are going to be PD or you are going to be in DFT or you are going to be in verification. So you spending time on this and understanding not only going to help your interview, even during physical design also this basic knowledge would actually help you a lot. Okay, so basically these are interview questions, and I want you to write it. All the assignment needs to be taken it seriously, and as I said, please submit the assignment by Saturday 5 p.m. Okay, and there would be a marks. So in the end, I would be looking at how punctual you are and how are you able to So these are all some things that indirectly that I would be looking at. Okay, you are on time submit. You're submitting on time or not. Remember, the reason why I'm putting all this is there will be some companies when I send your profile. They would ask, Kumar, give me top 5 guys. So there could be, say, 10 guys who would be looking for a job. I might have 10 people resume. But if they would be asking me kind of, Kumar, I may not be able to go and talk to all 10 people, but I have a two openings. Give me top five guys. I'll shortlist two from that. Now, how will I shortlist the top five? Depending on all this. So how much effort are you putting in your, the assignments, lab assignments, theory assignments? Are you on time submissions and everything? And even if you're a relative of mine, that will not be considered. What I look for all is submitting assignments on time and being proactive, helping others. So basically, you need to showcase yourself in the group. Okay, so you need to be in limelight, or probably you have to keep yourself active in the group, help others, post some or other things. You are free to do anything in this group. There is no restriction. So assignments has to be on time, and you will get these questions every Tuesday by end of Tuesday. Okay, so you'll have enough time. Okay, all right. So that's all on the previous things and assignments. We'll give you a minute. If you have any questions, we can talk. Otherwise, I'll have my own, plans for the day. Any questions or anything that you want to ask? Whoever is working on that block and anything that they can work during, synthesis, the synthesis engineer will have to do that. And PD engineer, anything that whatever that he, so at the end of the day, PD engineer is the last guy who would be, taping out. So irrespective of whether synthesis person is actually, going to work or not, end of the day, it falls on the PD person. Obviously, yes, yes, yes. Okay, all right. Just give me a minute. Okay. Before we get started on actual topic, okay, I want to just give you probably a food for thought, which is something that you can go back and just understand what is the meaning of big little processing, or big little architecture that ARM have brought in. Okay, so now what is this meaning? See here, introducing big little architecture uses the right processor for the right job. Okay, now it's up to 70% energy savings on common workloads. Okay, now flexible and transparent to apps, importance of seamless software handover. Now, if you look at right, as I said, so you have a CPU, which is kind of this to CPU, which is kind of high performance CPU, and look at this. These two are kind of low performance CPU. So any heavy workload, say for example, you are playing a games, or you're editing something, or some high-end games, or probably graphics, it's dominant apps that you are using, or any of those things. Now, so any kind of high load would be handled by these high performance cores. Okay, now so when your mobile is kind of an ideal mode, or probably ideal to little usage. Okay, so it would be using the cores from this one, so that way during the ideal time this CPUs would be turned off. Okay, This would be turned off. Okay, now during high performance, this would be kind of ideal left over, and this would be kind of handling all the kind of jobs. Now to get this done, okay, now to save your power, what is that you have to what kind of implementation architectures or implementation styles that you need to follow. So you guys might wanted to go back and explore, so that would give you a rough idea. Okay, so it is something that we call it big little processing. Okay, now so this is the Wikipedia page. You don't need to go anywhere basically. See here, this is what I was just talking about. If you see a quad core or say octa core, okay, it is going to be kind of four high performance core. So remember here, either this four or this guy. Remember, it is something like Linux schedulers, and fix one cluster at a time and no combinations. So these are all too much in depth of it. How they operate, will they operate to both, all the four at the same time, or one would be picked depending on the load. The next one would be picked. So how the way the whole CPU is performing. Okay, so this is something that if you are really interested to become a CPU engineer, you having a knowledge on this architecture is something you don't need to know, but just to understand that, okay, four high performance core and then four low performance core, and when they operate, and how do they operate, and etc. That's enough. Okay, this is another kind of example, and you do have your see here. This is another example. Okay, so now food for your thought. Okay, what are all the optimization methods? Or okay, so let me give you. You can go back and research this. Okay, so the context is basically CPU. Okay, say ARM CPU. One is basically you targeting your timing. Okay, when you say timing, this is basically 3 gig. Okay, now what are all the implementation guidelines? What are all the implementation guidelines? What are all the implementation guidelines that you need to follow during, say, when you say you are working on a high performance core or high performance design? What are all the implementation guidelines that you need to follow if you have to achieve 3 gig? Okay, now that is one. And the next one is basically targeting your power. Okay, so targeting your power. Okay, what are all the low power, low power methodologies? Okay, what are all the low power methodologies that are used, or probably that are available and used at the time of implementation? during implementation. Okay, so this is something that you can go back and start looking into it. There's going to be a big topics, and we will cover so all of them. Okay, so during our whole course, so we will get to know each and everything. So let's say if you wanted to target, so when you say power, you should always do not look at your in total power or something. You should always look at static power. What are the things that you can reduce? Now dynamic power, what are the methods that you can reduce? Now, can you apply them? Is it practically possible? So some of them, maybe people call it like kind of it is always there in the IEEE paper, but it is not possible to implement in ICs. Okay, so if you look at most of the researches, there may be 10 researches that would be paper would have been published, but will I be able to go and implement all those in my design? That is something that I may not be sure, but there would be some five or six that would be easily implementable. Okay, okay, all right. Moving on to our regular topic. So let's talk about. I know I need to cover this second order effects, but since this is being the last class for everyone, from next week onwards, I would be moving to the closed group classes. So I would be explaining you at that point of time, because I wanted to give you guys how to design the circuit, and I wanted to cover this so that like you learn much more. The second order efforts you can also go and learn yourself. Okay, now this particular slide talks about the CMOS inverter. Okay, now when I say CMOS inverter, you guys know that your PMOS is going to be on the top and NMOS is going to be on the bottom. Okay, now the moment when you give, sorry, before I go there, did we explain this slide? I don't want to spend time if we have already covered the slide. Yes, I can give you a little more stuff. Did we cover the slide with all the kind of inward covered, right? So did we talk about that voltage curve? So V in, V out, and all of that. So it is going to be say something like this, and then did we cover all this? Okay, great. Then fine. Let's just skip. Okay, so schematic is going to be something like this, and your symbol. This is your gate. So remember, this is your schematic. Okay, and this is something that we call it a symbol or gate. Okay, now the next important thing is your layout. So the layout is what we actually go and manufacture. Okay, now you might say that Kumar, this is how the inverter looks like, but in IC, if you get a chance to reverse engineering an IC, okay, the silicon will look like something like this, the inverter. So this is something like in terms of your schematic and gate, and this is your something called layout. Okay, now when I say layout, at the end, the goal is to convert each and every circuit into shapes. So ideally speaking, this is going to be your poly. See, this is going to be your poly, and this is going to be your OD. Okay, this is going to be your OD, which says, this is what decides your overall transistors. Now, these are all the shapes that gets manufactured as similarly exactly what you see here. And then here, this actually behaves like kind of a transistor. Now, if you guys look at, this is your, say, kind of, NMOS. So We have covered about this NMOS in the first class or second class. Okay. Uh, if you look at, there is something called poly. Okay. And then you have something like kind of, OD. Okay. So now if you look at your transistor, we have different terminals. Correct. Now this is going to be your, see, source, and this is going to be your drain, and this is going to be your gate. Now your transistor is basically, we need to convert it as a, the layout, and this is how it is going to be. Now if you look at this, this is something, this is something that we call gate. Okay. Now you can pick, this can be source, and this can be a drain. Now the beauty of your MOSFET is basically the source and drain can be interchanged. So this can, if you treat this as a source, this side can, work as a drain. If you treat this as a source, and this side can work as a drain. Now if you wanted to choose this as a source, you can go ahead, and this side will operate as a the drain. So the beauty of this MOS is your source and drain can be interchangeable. So it need not be that the left side is the one which is always source and right side is the one always drain. So there is nothing like that. So your source and drain can be interchanged in the layout part. Okay. Now this NMOS, okay, being converted as a layout here, and this PMOS is kind of, converted as a layout. Now remember, when you say transistor, it is always what layers that we call it. So this is basically poly layer. It's called P poly. Okay. Now this is something that we call it OD, oxide diffusion. Okay. And this is what actually, we call it. This particular thing is nothing but your length, and this is basically your width. It's basically your width. Now, what is that layer? This is oxide diffusion. Oxide diffusion. Okay. So any transistor that you may see, any kind of, schematic. Now in the layout, if you see this kind of thing, basically your OD, on top of it poly, then only the transistor is being formed. See, you have a OD, but without poly, there is no transistor. There's no transistor. And these two shapes, you know, exactly this. This is what actually forming a transistor on the chip. Okay. So we'll talk about more, we'll talk more on this. But before that, let's go and try to, understand a little more on the schematics part. Okay. I think we talk about this? not sure. I don't recollect. NAND gate operation, NOR gate operation, and how they operate, and etc. I doubt. Can someone confirm? Okay. Okay, great. So that's fine. Uh, Now, what we will do is let's try to spend time on how do we come up with these schematics. Okay. Now, so how do you design the schematic? Say, for example, now NAND gate. Okay. So what is your equation? AB whole bar. Correct. So it's AB whole bar. NOR gate it is A plus B whole bar. Now remember, do you remember the inverter? CMOS inverter. So basically A bar. Okay. Now by default, the CMOS structure will have a inverting in nature. So if you look at this, so this automatically it is going to be say kind of A, and this is going to be say A bar. Now how this is actually happening? This is actually kind of inverting in nature. Correct. Now remember this, when you wanted to when you want to draw a circuit or schematic, any equation, if they give you bar, if they give you bar, okay, just ignore the bar. Okay, now what is the equation that you will have left with? AB. Now implement this AB in the pull down. Okay, when you say A and B, that means it is going to be parallel. So just look at this kind of parallel. Now say this is going to be kind of A, and say this is going to be kind of B. Okay, now when it comes to the pull up, okay, anything that you have in parallel here, that has to be kind of sorry, anything that is in series here, it becomes a parallel. It is exactly opposite. So it is kind of B and A. Now just have to connect this to VDD, and this is going to be connecting to VSS, and this drains. It is going to be always Z. Okay. Now, so this is what we going to follow when we are going to design a schematic. Now, for NAND gate, why I said removing the bar, because by default they are inverting in nature. Okay, by default they are inverting in nature. Now, so for NAND gate, by default you would be able to implement a NAND gate. Now, if you wanted to implement AND gate, what is it you need to do? What is your equation? AND gate equation is AB. Okay. Now, how this can be converted? A double bar. No, AB double bar. Now you can go and build the equation for this first, and then you need to build another equation, basically another circuit like this. We'll talk about more on that. Okay. But let's understand the NAND gate first. Okay. Now, as I said, A and B in series. That is basically and. It's kind of and meaning. A dot B is the meaning, and then this series becomes a kind of parallel on the pull-up side. Okay. Now let's go and quickly, write the truth table for NAND gate. So 0 0 0 1 1 0 1 1. What is the answer? Output? And someone quickly tell me. 1 1 1 0. Okay, great. Now apply this and see if you are getting the same results. Let's just apply 0 0 1 1. What is happening to the transistors? This is on and this is on. And what about these guys? Off, this off. Now look at, so these two are off. There is no way that it can discharge to ground. So there is no way that it can discharge to ground. Both ways, both of them are off. Now look at this guy on, this guy is also on. Now, so there is a charging path. Yes, both the transistors are on and so they are able to, they are going to charge. Now this is going to give you output of 1. So is this clear? This particular thing is verified. Okay. Now coming to the second one. Okay. Now coming to the second one. What is the second one? B is 1. Okay. And B is 1. So A is basically 0. Sorry, my bad. It is like that. Did I write here 1 1? Now, in case of A equal to 0 and B equal to 1, now analyze. A is 0. So that means there is no path between your out to ground. There is no path. Okay. Now look at, because A is off. So since this is being off, you don't have kind of direct path. Now look at here. So A is on and B is 1. This is basically off. So, but because of this transistor is on, it can go and charge the cap. So that means this is also kind of 1. Okay. Look at the next case. It is a 1 and a 0. What is it going to be? Say A is basically 1, B is 0. So remember, so this is 1 and this is 0. So this is going to be off. This is on. This is on. And this is off. Now look at it here. So is there a direct path here to here? There is no direct path because there is off here. This transistor is basically off. So this is kind of broken. There is no direct discharge path. Okay, fine. We verified on the bottom side. Now go and look at here on the top side, which is kind of VDD to out. So there is a on, the B transistor is on, A is basically off. So there is a path. So this is going to be 1. Okay. Now coming to the last thing. Okay. So assuming both A and B are 1, what is it going to happen now? So it is going to be kind of both PMOS are going to get 1 1, and this is going to be on, this is going to be on, this is going to be off, this is going to be off. Okay. Now if you look at here, is there a path, direct path from this out to ground? Because both the transistors are on, it is there is a path. So that means this is valid. Now come and look at here. So this is off and this is also off. So that means there is no charging path. So only there is a discharging path. That means zero. So this is how you should actually, come up with your circuit and verify that, with the truth table. So this is the way, you should, explain in case if you are attending interviews or if you've been asked to. Okay. So any question on NAND gate? So we had the equation, Boolean equation, and based on that we have drawn the circuit. Now that whether the circuit that we came up as actually working as per the spec or not, that we have verified it with the truth table. Okay, I'll give you a minute. If you have a questions, you can ask me. Yeah. Yes. Yes. Okay, I get your question. So what is your question is basically you have a two input NAND. Okay. Now, so there is a three input NAND and then you have a four input NAND. Okay. Now your question is which one say in case of different requirements, design requirements. So let me tell you that in your design library, so basically you will have all this kind of cells that are available. So NAND with two inputs, NAND with three inputs, NAND with four inputs also available. Now remember one thing. Now this cell propagation delay is kind of say uh, 50 ps. Okay, NAND 4 propagation delay is kind of say 50 ps. Now look at NAND 2. So you are going to implement the same thing. I need to verify the functionality, but definitely you need minimum two stages. Minimum two stages, or probably you might end up in adding one more inverter or something, which I need to check. Now, if you look at these two guys, will take kind of 30 ps, propagation delay. If they are kind of going to have a 30 ps delay, and this is also going to be having a 30 ps delay. Now, if if at all, if you end up in adding one inverter here, as I said, I'm not verifying the functionality now, just for the sake of explanation I'm giving you. Now say if this is going to be another 10 ps, now you would end up in having minimum 60 to 70 ps delay, overall. And also if you look at, there's a logic level 1, logic level 2, and logic level 3 in case if it all you have to add it. Now the answer is going to be depending on my you know uh, frequency of the design. My tool might pick kind of four input NAND, or it can pick three input NAND, or it can even optimize this four inputs and might be converting this four depending on the inputs, what kind of inputs, and if there is a kind of constant, if there is any kind of constants and etc. So it might optimize the cell, but we always try to prefer in this scenario and NAND 4. To answer your question, we prefer in case of NAND, we don't have any problem, but in case of NOR 4, we have a problem. We don't prefer NOR 4 in our designs, so we have to cascade it kind of stuff. But NAND, we have no problem in increasing the number of inputs. Did I answer your question? So remember, there could be some design, scenarios where you may not want this multiple logics. So this all things coming in within a cell is going to help your overall performance of your design. You will understand probably when I move to your place and route topic, placement of cells and routing. So that time you would understand what I'm talking about. Okay. Any other questions on this NAND? Now you guys are going to explain the NOR gate here. Okay, NOR gate equation is this. Now remember A dot B meaning it is kind of series. Now A plus B meaning it is kind of parallel. Okay, now this parallel thing becomes a kind of series on the top. Okay, now can we quickly check? Say A, B, say Z. What is it going to be the truth table? Okay, great. Now, so let's talk about the first scenario. So A, what is going to happen to your transistors on the PMOS side? So both A is on, this also on. Okay, so there is a direct path, charging path. So likely that it would be 1. Now, what about your pull down? This is going to be kind of, say off, and this is off. So your answer is kind of, verified for the one case. Now, what about the second one? Anyone else? Okay. So it's basically B is going to be kind of, off. So this is going to be on. So this is going to be off and B is going to be on. Now, if you look at, there is a direct path, discharging path. Now that means, and you also go and check it over on the pull up, there is no direct path to VDD. So there is no charging path. So your output is going to stay at 0. Okay. Now what is the next one? Anyone else? Come on guys. We have many people here. So this is going to be on and this is going to be off and this is going to be on and this is going to be off. Now, so you have a direct path, discharge path is present, but no charging path. So that means your output is going to be staying at 0. Now the same case on the last one. Okay, it is going to be both are 1 1. So both the NMOS are going to be on. Okay, so there will be a discharge path and there will not be any charging paths. Okay, so they are working as per your spec. Now the question is, I'm not sure if you guys remember, I asked you guys, is NAND bigger in terms of area or AND is bigger in terms of area? During the digital, I asked this question, if you try to recollect. So usually in our textbook, we always talk about AND gate first and you adding an inverter, and we call it, this is something that it's kind of, NAND gate. Okay. Now, so tell me which one is going to be higher in terms of area. So by default, NAND, two input NAND is having, two input is NAND is having 4 transistor. Okay. And now two input AND meaning, what is that you need to do here? Extra an inverter that needs to be added. So ideally speaking, So you need to add an extra inverter to make it as an AND. Okay, now, so two input AND will have how many transistors? Six transistors. Okay, now eventually by looking at this, okay, you can easily figure out that NAND is going to have a lesser area compared to your AND. And this is possible. This is the the statement is true only in case of CMOS style. Okay, the statement is true only in case of CMOS case. Okay, and remember the best circuit that you can have is, say, number of inputs into two. That is the best thing that you can have, but not possible always. Now in case of AND, because you need to add one inverter extra. But if you are okay with that, inverter kind of things, the bar, the best possible scenario that you can have is basically into number of two transistor, basically the number of inputs into two. This is going to be a transistor count that is going to be ideal. Okay. So any question on this whole thing? Okay. All right. Now, so you can now ask me questions. Now, in the meantime, now food for thought. So we know there is a NAND gate. Now, say A, B, and Z. So we talk about always cell delay, propagation delay. Correct? Yes or no? Now, do you think the delay between A to Z or the delay between B to Z is going to be same, or are they going to be different? Okay, so that is one. Now, what about your power consumption? Reason? Okay, Aruna, I'm not going to let you answer from here onwards. Okay, I know, I know you. I'm giving this to the others. Okay, okay. For your information, others, Aruna, I know him since 8 years. I think 8 or 6 years. Okay, so I know him 4 years. Yeah, right. Yeah, 4 years. We know each other, and he's here to brush up his knowledge. So he already knows, the concepts behind it. So, but this for others. That's what I was just wondering. Because a person, unless there is someone from industry, they won't be able to even distinguish this. Garden, garden. No, no. So this is something that I want the others to think and answer. So from next week, you are allowed to answer because we will be moving on to the actual topics. So that is going to be, you can add your points over here. So the food for your thought is basically figure out A to Z, will there be a different propagation delay, and B to Z, will there be a different propagation delay in terms of delay in both the cases. And what about your power, overall power consumption? Okay, so uh, spend some time, you will get lot of ideas, or probably you will learn a lot more. Probably if you're able to learn that level, that's what you actually need to get into industry. Okay. Okay, so this slide talks about exactly the same thing that we have discussed. So PMOS, if it is in parallel, your NMOS is going to be kind of in series, and if NMOS is in parallel, and PMOS is going to be in kind of exactly the series. Okay. Okay. Uh, okay. Can I guys tell me the equation for the first one? Since you guys have gone through the basics now, let's do some class work. What is going to be the equation? Z here. What is the equation? So you have got four variables. Now, okay, A into B plus C, and then plus D. That's it? Or whole bar? Okay. Okay, so this is the one answer that I have got. Any other answers? Okay. Any other answers? Okay, so this is correct answer because if you look at right, look at this way. So A, the first element, so it's basically A. Now this is in kind of series, so that's basically dot. Now these two guys are in parallel. It's basically B plus C. Now, so you have done with your first portion here. Now there is another parallel this, which is basically kind of say D, the whole thing. Okay. Now look at this particular diagram. How many transistors that we have here? How many transistors we have? One, two, three, four. So as I said, we have got four inputs. So you have got total eight transistors, four NMOS and four PMOS. Okay. Now let's move on to the next problem. Okay, so this time I want others to answer. People whoever has answered till now, please excuse this time. Others who have not answered, yeah. Okay, A plus B into C plus D. Okay. Any other answer? Okay, great. Okay, yeah. So this is your correct answer. Now let me give you. Now the homework is basically I want you to draw circuit for all this. Okay, so this is going to be a homework. So I want you to draw circuits for all these equations. Okay. Okay. All right. So I'll anyway send this in particular thing in Telegram group. Okay. So you guys don't need to note it down. Okay, all right. So now moving on to the layers part. Now, see, you guys have to understand one thing here. So VLSI is basically the overall, right? If you look at it, it's kind of stack one layer, then there is a kind of dielectric or kind of an insulation layer, then next layer. So if you look at, you guys know the sandwich, the burgers or sandwich and etc. Right? So what is that? You would see kind of a bottom one layer. Okay, so they add something again, one more type of layer, one more layer, one more layer. So in the end, if you look at these are all kind of one after other kind of sandwich structure. Okay. Now the same thing is what we actually follow in our VLSI. Okay, or probably in the semiconductor as well. Now you guys know that your base is kind of we call it silicon. Okay, so your base is silicon. Now on top of it, you try to bring all the layers that going to help you to fabricate PMOS and an NMOS. Okay, that is going to help you to manufacture PMOS and an NMOS. Okay, now in that process, if you look at, there are something called layers. We have a different layers. Now this is exactly what we call it in the industry. It's called mask. Okay, now if you look at, so these layers, okay, so we have something called N well, P plus, N plus, oxide, poly and contact. So these layers are known as base layers. These layers are known as base layers. Okay, and now these base layers are used mainly for fabricating a transistor, or they are they definitely they need- you need them, otherwise you cannot form a transistor. Okay, now these metal layers, so you need to understand there is something called, okay, so for example now you have an AND gate. Okay, now AND gate is going to see an OR gate. Now this transistor, okay, the AND gate is basically you know uh, formed or probably fabricated with the help of these layers. Okay, now your metals, okay, is going to be used for this interconnects. Your metal layers are going to be used for this interconnects. Okay, so that is a basic thing that I want you to understand, have it. Now, so once you manufacture, to manufacture the basic transistors, you need all these layers. Okay, now to connect those output to the input, basically we call it net, or people call it interconnects. Okay, so this is something that we are going to use the metal layers. Okay, so remember in industry we have a naming convention which is called FEOL. It's a front end of line, and which is basically the base layers, and all the metal layers would be known as back end of line. Okay, so remember base layers are the one which actually forms a transistor, or used to form a transistor, and your metal is the one actually used to connect the pins, or probably the physical wiring, or you can call it. Okay, so in industry the term we call it like kind of FEOL also, some companies refer it, and BEOL meaning it is a back end of line. Okay, so any question here before I move to the next one? Like, yeah, yeah, back end of line. We will talk about it more on it. So I would have to talk about the whole metals, and each metal will have its own characteristics. So all of that we will talk in the upcoming classes. So in case if you are curious, it is called redistribution layer. RDL is basically called redistribution layer. Okay, now let's understand why we need all these layers. Okay, so we talked about these layers, right? So we are talking about all these base layers and different types of layers. Okay, now look at this. This is your basically your silicon. Okay, so this is your silicon. P substrate is basically your silicon. Okay, on the silicon you can directly go and manufacture NMOS. So it's basically N plus. Okay, so this kind of N plus impurity addition, and you make it this as a kind of source, and this kind of drain. Okay, and this is going to be your kind of the gate. Okay, now this is your body or bulk. Okay, now if you look at this, so your P substrate, which is basically your silicon. Now this is basically your N plus. N plus, you have manufactured these things. Now your poly. Okay, so your poly. Okay, and now there is something called width. So if you try to imagine the 3D section of this is going to be kind of the width, right? Now that width is really going to be called oxide. So that width, the width is nothing but your oxide. Okay. Now, so for NMOS, what are the layers that we have covered here? So we have covered N plus oxide, poly, and so contact is something that we would be using it to connect. So if you guys look at a transistor, now we say the source is connecting to this VDD. Okay. Now this particular connection happens with the help of contact. So contact is something that kind of hole, which is going to be used to make sure your source to drain or any base layer to metal. So contact is basically connects any base layer to metal. So that is what we call it, contact. The purpose of contact is basically any base layer. If you wanted to connect any base layer to the metal, it's basically, it could be your input, or it could be your VDD, or it could be your VSS, or you might connect so this drain to this drain, and marking it as an output. So any layer, any base layer to metal. So the purpose of contact is that. Now that is your contact. Okay. Now the next one is coming to PMOS. Now we know that you need you cannot directly manufacture PMOS on the P substrate. Now, what is it you need? You need N well. So N well, once you manufacture your N well, that particular thing is ready for your PMOS structure. Now you go and bring your P plus. Okay, so the whole thing is NMOS, N well, where you are going to manufacture your PMOS transistor. Okay, and as usual, this is going to be your poly and the gate part. Now look at here. So N well is actually going to be needed for manufacturing your PMOS, and then your P plus eventually needed for your the P diffusion to form a PMOS transistors. Now, as usual, oxide is something that you really needed. Now, if you look at this, do you understand why we need all these layers for forming a transistors? Is it clear? Any questions here? So, without these layers, you will not be able to complete your you cannot manufacture any kind of chip. It's very simple. Now, what I'm showing you here is basically the inverter cross sectional diagram. Okay, but this is exactly how it would be in the silicon as well. Okay, go ahead. Go ahead. Go ahead. Go ahead. No, no, no. Wait, wait, wait. If your question is about oxide layer, I'll come to that later. Wait. Any other question? So no, I want you to first understand why we have so many layers. Ideally speaking, if you go and take a look at the number of masks, so each layer is called one mask. Okay, so for you to understand the whole process, I need you to go through the manufacturing process. So I want you to go through the manufacturing process. Okay, IC manufacturing process, say CMOS manufacturing process. Now you guys also know that what kind of family is this? Bulk. There are three different process. One is bulk process, next is twin tub. Okay, and there is a one more which is called SOI, silicon on insulator. Now, so we don't see bulk process is the much kind of very well used at this point of time. Twin tub meaning they would actually go and manufacture P well also like this. Okay, so that is a difference, and we don't follow this. Now, SOI is something that is a different technology altogether, which is known as silicon, basically, which is kind of uh, for this particular technology is actually there is a company called Global Foundries. Global Foundries. Okay, so they actually focus on FOI technologies. Basically, they call FDSOI, fully depleted SOI. So it's basically 22 nanometer or 14 FDSOI, something like this. Okay, so FDSOI, basically SOI is also there, but not much. But bulk is the one which is kind of dominating. Okay, so go and spend some time. And I always suggest, I think I'm not sure if I have given this book. So CMOS VLSI design by Weste and Harris. Okay, that's a book that I follow. Weste and Harris. So even now I have a hard copy and I use that. If I have to take any interviews or if I if I'm giving interviews, I just brush it up. Or even there is another book, Rabbi. Uh, I have not gone. I gone through it maybe in the initial days, but somehow I kind of like Stay and Harris. So this is what something that I follow. So it's up to you. But if you ask me, Kumar, which one would you suggest? I suggest this one. Okay. So the first three chapters, 3 or 4 chapters, where they talk about basics of whole CMOS, that would actually gonna give you a lot of idea. Okay, so you might have gone through those books in the past also. Now look at, so the way we are talking, right? Say power, let it be a power, or let it be a structure, how they are getting manufactured, what is the meaning of mask. Now why we say something called a contact. Now what is the difference between contact and via. Okay, so now the way you are going to read it now is going to be totally different. So now, see, you might have read from exam perspective or concepts perspective, but now you need to look at how a silicon is getting manufactured. So the if you keep that in mind and if you go through that book now, I'm sure you will probably, learn. Probably you will open up a new, area, or the way you look at it is going to be different. Okay, now moving on. So the base layers are this one. Now interconnects. Now metal layers. Now remember, we talk about the interconnects. See, it is now look at this. So this particular thing you need to connect. The PMOS thing is going to be connecting to your VDD. Now this is going to be connecting to say CA input A, and this particular guy you are going to connect it to VSS, and this two you are going to connect it to something called Z. Now anything that I drawn in this blue color, okay, they all come under interconnect. Okay, all this would be eventually you need to use interconnect layers to establish the connectivities. Okay, now when I say interconnect, now remember which layer is going to be resistive in this case, which is base layers are going to be highly resistive or metal layers are going to be highly resistive. Think, why are we using metal layers for interconnect? Can't we? Yeah. So basically, you cannot use your base layer for implementing this connectivity or the interconnects because they are kind of high resistive. Okay, or probably they need some extra force or something to make that work. Now metal is the one which is kind of low resistivity, and it is going to help you overall your propagation delay. So remember, anything that I talk here, it is always going to be PPA, power performance area. Now, when it comes to performance, say this is 30 PS with the metal. Now, there is a same inverter with a different set of layers. It's 50 PS. Now, which one I would use? Assume you remember you are working on 2 gigahertz design. So, which inverter would you prefer? The one which is giving you 30 PS. Okay. Now, having said that, we always prefer less resistive interconnect material. Now, so we are going to use these metals for the connectivity implementation or the building one. Okay, and your metal is the one which is going to have a lower resistance. And now the food for thought is, so you have different metal layers. So metal one is close to the substrate. So remember, metal one is going to be the close to the substrate. Now metal, the higher the metal, they are far away. Okay, say M10, that is going to be kind of far away. M1 is going to be the closer to the substrate. Now the homework question is, among these metals, which is going to be high resistive, which is going to be low resistive. Okay, among these metals, which is going to be high resistive and which is going to be low resistive. And if you wanted to understand that, you need to go and look at it, something called metal stack. Okay, something called metal stack in VLSI. Okay, let me see if I can just give you guys so that you can go and read it. So exactly you get an answer, your whole answer is here. Okay. If you go through this particular website, you will get the whole answer for the homework that I gave you. Okay. So there's something called metal stack, and lower metals and higher metals. Among them, there are different layers which is going to be having a different resistance. Okay. So here you go. So this picture would give you the whole the answer for the question that I gave you. Okay. Now moving on to the next one. So any question, and remember, and we always have metals. Say for example, M1 is basically horizontal, M2 is kind of vertical, and M3 is going to be horizontal, and M4 is going to be kind of vertical. So it is something we call it HVH. So all the odd, basically you say M1, M2, M3. So remember, and we do have M0 also these days in the lower nodes. The first layer, let it be M0, or if M1 is your first layer, the first layer is going to be always horizontal. Okay. The next layer is going to be always kind of, vertical. Now, if I have to show you what is the meaning of horizontal and vertical, let me just bring up the tool. So the question here is why we have to follow alternate direction, different directions for each layers. Why not follow all the layers can have a same direction? Why can't we follow the same layers for all the same directions for all the layers? What is it disadvantage? I don't know. Work on and put it in the group, please. There may be many answers, not just only one. So if you look at your standard cell rails, okay, so they would be kind of M1 first layer. So in this process, we have a M1 which is kind of horizontal. Now let's go and take a look at your layer 2. Do you see any kind of horizontal routing here? Do you see any kind of M2 which is kind of horizontal? So this is, let me remove M3. Do you see any kind of M2 which is horizontal? What is the layers that, what is the direction that you see here? Vertical. Okay. Now, just remember this. Now I am going to enable M3. Do you see what is the direction here? Horizontal. Exactly. Yeah. So now, what is the reason behind we following? So alternate layers will have the, basically each layer will have a different direction. So alternate, basically HVH or VHV or whatever it is. So HVH is something. Now, what is the main reason for this? You guys go and do some kind of research, but eventually this all would be covered in art classes. Okay. Okay. The last topic for the day. Maybe we'll try to spend some, you know, uh, quick time on the inverter, and we'll wind up for the day. Let me just pull up. Okay. Now let's take a look at this inverter. You guys know this is a schematic. Okay. And now understand that your cell size. So this is going to be your cell size. Each cell will have its own size. So depending on the number of transistor, each cells will have its own size. Now, if you look at the tool that I was just showing you guys, okay. Now is going to have that particular thing is going to have, each standard cells, they are all kind of equal height. Do you see here? This is the kind of height. Now, irrespective of the cells, whether it is AND gate or OR gate, you see here full ladder, NAND, OR, NOR, NAND, and all of that. So they are all going to be kind of, having same height. Okay. Now that height is going to be same for all the kind of standard cells. So that this is going to be your cell area. This is going to be your cell area. Okay. Now your transistors. Look at this. As I said, you need what layer? So assume this white background is your silicon. Now N plus can be exactly manufactured on the P substrate. So you have a N plus which can be manufactured easily on the P substrate. Now to manufacture PMOS, you need something called N well. Okay, so you first prepare N well. Okay, N well is something here, and the of once you manufacture your N well, the first thing is going to be your N well. Now next N plus, and at the same time next is going to be your P plus. So now basically what you have done is you have prepared area for your NMOS and PMOS. Now remember your transistor. So each transistor will have its W and L. So now this is going to be your L. Okay, and this is going to be your W. Okay, so depending on your NMOS WLL, you come up with this particular, say something like this. Okay, now this is going to be your L and this is going to be your width. So PMOS also you will have your things like this. Okay, now you have done with your simple skeleton circuit. Okay, simple skeleton circuit. Now what is the meaning of inverter? You connecting this to your ground, this source, and this source is connecting to your VDD. Okay, now look at this. So this is actually kind of in a source, and this is going to be treated as a drain. Now this is again going to be source, and this is going to be drain. Now what is it you have done? Your VDD metal connection that you have done, and this is your contact. So now basically this OD is nothing but your the thing which exactly same as your width. Okay, remember this is what the width is. So your P plus and an N plus would be on the complete area. That's kind of the flow for you. Now OD is what just we call it like kind of the exact the size of that OD would be exactly the same as the width. Okay, now your source, and this is going to be your drain. Now source is connected to VDD, which would be kind of you will have your standard cell rail. Okay, and you will also have your VSS, which is also kind of called standard cell rail. Now the source, I'm connecting it to VSS in case of NMOS using the contact. What did I tell you? Any base layer that you want to connect to metal, you have to use contact. Correct? So use this contact and you are connected now. So what did we do? We have implemented both VDD and VSS side. This and this are we are done now. Now next thing is both the inputs are shorted. Do you see this? Both the inputs are shorted and we give it kind of A. Now look at this. This poly and this poly are basically now become one single poly. If you look at this becomes a kind of one single poly. Now the A is going to be kind of metal, which is we are connecting it to that poly using the contact. Okay, now you are done with this particular connection. Now the next one is your drain. So basically now you need to connect these drains, both the drain, and you need to mark them as a Z. Now look at this. This is your drain and this is your drain. Now connect both of them and mark it as a Z. Okay. So now whatever that you see here in the schematic, did we connect everything properly or no? Do you see everything connected properly here in this circuit? You can just take a look at it this way. See here. You see this? Any confusion here? Now, sorry? Yeah? Yes. No. Wait. I don't want you to tell me upper part, lower part, and all those things. You need to always use what transistor it is. It is basically a PMOS source that is always connected to VDD. Now, what's your confusion here? No, I do. Drain is never connected to VDD. I said only source. So I drawn it here clearly. This side is source, and these two are drain. Didn't I? I did. Any other question? So basically, when you are going to when you have to understand the layout part, take the schematic first, then draw a skeleton, you know, transistors, and then you need to just start connecting them based on your schematic. And remember, this do not refer any books for your layouts. No books, please. All your books are whatever that they say. It is all outdated, and the layouts that you see in the books are going to be totally different than what we do in what we use in industry. Okay, so my request is do not go and refer any books for your layout. So whatever that I covered, if you follow the simple steps, you're there. Yes. Yeah, right. That's what I said. No, PMOS meaning it's going to be always this side only, because that is the only area that connecting. No, correct. Yeah. No, no. See, they are all different layers, right? You remember one stack here. Say your first bread, then your veg, vegetables, and then you have your cheese, and then things like that. So now, would you say all of them inside bread? No, right? So they are all kind of at different higher level. See, that's what I said. If you guys wanted to understand, you should go and look at your the stack, this particular thing. Now, what did I tell you? So your source of this PMOS is going to be connecting to overall high, gonna have come up all the way till upper layer. And you guys remember in IC, you will have one VDD, and you will have one VSS, and you will have all the inputs and outputs and etc. Correct. So end of the day, this VDD pin will reach to your PMOS source. That is how it is going to be. You would be designing the chip. So remember, I mean, I'm sure everyone comes from your the electronics background, or I have an idea about it now. So VDD, you will have an IC pin. It's called VDD or VSS. Both you will definitely have it. Now this VDD eventually will reach to this source. Okay. Now, so to answer your question, are they inside your, in the envelope? I won't say it's inside in the envelope, but it is it comes mainly on top of the envelope. Okay. Yeah. It's going to be on top of the envelope, because envelope is going to be a bigger area, no? Correct. So don't, first of all, the question itself is something that I wouldn't encourage. The reason is, don't get into that kind of, whether it is inside this particular layer or what. No. Each layer is kind of, one stack. See here, now N well and P substrate. Now P plus and an N well. Now N plus and P substrate. So they are all kind of one after other. You understand, right? So remember the burger always. Look at this. What is this? So each layers, metal one, metal two, multiple metal. So these are all kind of stack. Okay. Now you see this particular thing. What is this? Do you see a stack here? The first layer, there is a next level, and there is a next one, there's a next one, and then there is a next one, and then seven layer burger, or make different layers. So that's exactly how your IC also going to be manufactured. First it starts with silicon, one layer, one layer, one layer, one layer, one layer. So something like this, there would be many layers. So that's what I always say. It is a kind of stack. Okay. I hope I answered your question. No, I don't want to keep this burger. I'll start feeling hungry. Any other questions? And let me tell you, you are not going to be a layout person. You are not going to draw this layout, or you are not going to design any of the cells. Okay, whatever that you see in this design. So these are all going to be inputs for you. Someone else will design all this, and that team is called libraries team. Okay, libraries team or IP team. So they are that would be kind of input to you. Okay, so but why I'm covering this, you having knowledge of this layout. Now the pin access, remember how this A going to be accessed from outside, how this Z is going to be accessed from outside. That you will be able to understand it better if you have the layout knowledge. Okay, so uh, try to go through little more on this. First, go and draw schematic. Now I'll upload this video anyway in YouTube, so you guys can just go and refer this and try to come up with your own uh, layout, and this will actually help you uh, to become a good PD engineer. Okay, so I do have a lot more topics to cover, but I think we were running short of time. So we'll stop here for the day, and so this is the last class for everyone. Whoever have not enrolled, in case if you are interested, please do enroll. Uh, and we already have the group Telegram group, which is very much functional. People are sharing their assignment questions. I mean, I'm sharing assignments, and then they are posting their assignment answers and everything. And we have already started Linux. Um, so this week there would be some Linux things and all coming up. Okay, so in case if you're here just to learn these two topics, I will be, I'm okay. Uh, Go and practice, and you will learn much more. And okay. So I'm done for the day. And any questions on these topics, I can answer. And for the guys whoever have enrolled, we will talk about the second order effects and little more in depth on this layouts and what is the meaning of fingering, and then you know uh, why we have a height is constant and width is gonna be more. What is the reason behind and all of that. So if you look at this cell, you see this height is kind of constant, but this width is bigger. So this cell width is smaller. This cell is kind of medium. And see here, this kind of bigger. So why these are all happening? So this all we will cover in our next class. Okay. So you will eventually start looking into these tools and everything. Okay. Any questions?